Welcome to this new video about asymptotes. So the question here is find all vertical and horizontal asymptotes for three functions. But before starting our work, I will try to make a quick reminder on the method how to find vertical and horizontal asymptotes. Let's start with vertical asymptotes. First of all, you have to identify the points where the function is not defined. Okay, so first of all, find the domain of your function. Okay, because by finding the domain, you're going to identify the points, okay, where you may have vertical asymptotes. So find the domain. And second step is to compute the limit where the function is not defined. Where the function is not defined. Okay? Then you can conclude if you have a vertical asymptote or not, because if you compute the limit of f of x as x approaches a point A where it's not defined, and you find that this limit is plus or negative infinity, you can conclude that the line x equals A is a vertical asymptote. Okay, so the procedure is very simple. First of all, identify the points where the function is not defined by finding the domain of your function. Then compute the limits where the function is not defined. It means at these points. And then if the limit is infinite, it means plus or negative infinity, you conclude that the equation x equals A is a vertical asymptote. Okay, this is for vertical asymptotes. But what's about horizontal asymptotes? For horizontal asymptotes, you have to compute two limits. The limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. Okay? Now, if you find that the limit at infinity or negative infinity is equal to a constant b, then the equation y equals b is a horizontal asymptote. Okay? Same thing here. If you find that the constant is the limit here at negative infinity equals b, it can be the same or something else, another constant, okay? But it's not infinite, then you conclude that y equals b is a horizontal asymptote. Okay? So this is the procedure how to identify or how to find your vertical and horizontal asymptotes. So let's start with our first function. We have f of x equals 5x minus 1 over x. I will start by identifying the vertical asymptotes. And remember that the first step is to identify the points where the function is not defined. Here you can see easily that it's a rational function, though, so the denominator must be different, not equal to 0. So x is not equal to 0. The domain is the set of all real numbers except 0. So if you have vertical asymptotes, it's going to be at x equals 0. Second step, you compute the limit of f of x where f is not defined, which means x equals 0 when x approaches 0. And this limit is equal to 5 times 0 is 0 minus 1, which is negative 1 over 0, because the x will approach 0. Here, it doesn't matter if it's 0 plus or 0 minus, since you are sure that this limit, which is a constant over 0, will give you an infinite limit, plus or minus infinity. Since the limit at the point 0 is infinite, then you conclude that x equals 0 is a vertical asymptote. Okay? If you have more than one point where the function is not defined, you have to check all your limits at these points. Okay? Now, let's move to the horizontal asymptote. And here we're going to compute the limit of f of x at plus and negative infinity. So let's start with the limit of f of x as x approaches infinity. And here we're going to use the leading terms rule, okay? Because we have a limit at infinity. So it's equal to the limit. The leading term in the numerator is 5x. The leading term in the denominator is x, okay, as x approaches infinity. And here we can cancel the x, and the result is 5. Since the limit at infinity is a constant, then the equation y equals 5 is a horizontal asymptote as x approaches infinity. Okay, so you have a first horizontal asymptote. Let's check for negative infinity. It means the limit as x approaches negative infinity of f of x. Again, here we use the leading terms rule, and we'll find the same limit since the leading terms are the same, and it will give also 5. So again, here you're going to find a constant. So the equation y equals 5 is a horizontal asymptote as x approaches negative infinity. So we have a common horizontal asymptote at both infinity and negative infinity in this case, and it's the case of all rational functions. If you have horizontal asymptotes, it's going to be the same at infinity and negative infinity. Okay? So let's move to the next function. Here we have f of x equals x squared over x minus 3. It's obvious that the only point where you may have a vertical asymptote is x equals 3, since the domain is the set of all real numbers except 3, which makes the denominator equals 0. Vertical asymptotes. So I will write it quickly. The domain is R except the point x equals 3. So we have to compute the limit of x squared over x minus 3 as x approaches the point 3. And here, if you substitute your x by 3, you're going to find 9 over 0. And you know that a constant over 0 is infinity. So plus or negative infinity, I don't care again, since I know that I'm sure that it's infinite, okay? So the equation x equals 3 is a vertical asymptote. Let's check for horizontal asymptotes. So we're going to compute for horizontal asymptotes, we're going to compute the limit at infinity and negative infinity. And here we have to compute the limit of x squared over x minus 3, our function, as x approaches infinity. Again, here we can apply the leading terms rule. So the limit as x approaches infinity of x squared over x. The leading terms are x squared and x here. And as you can cancel the x, it's equal to the limit of x as x approaches infinity. And this limit is infinity. So the limit at infinity is infinity. It's not a constant. So no horizontal asymptote as x approaches infinity. No horizontal asymptotes as x approaches infinity. We didn't find the limit at infinity equals to a constant, okay? Therefore, there is no horizontal asymptote as x approaches infinity. Let's check for negative infinity. So the limit, and I will do it quickly, it's the same thing. So the limit of x squared over x minus 3 as x approaches negative infinity, and it's equal to the limit of x as x approaches negative infinity, and it's equal to negative infinity. Therefore, again, no horizontal asymptote no horizontal asymptote as x approaches negative infinity. Okay, so for this function there is no horizontal asymptote. Okay, now let's move to the third one. Here we have f of x equals x squared minus 1 over x squared plus 2. First of all, let's check for vertical asymptotes. And again, to find the vertical asymptotes, we have to know where the function is not defined. So let's set the denominator of this function equals to 0 to find the points which make the denominator equal to 0. So let's write x squared plus 2 equals 0, which means that x squared equals negative 2. But this is never true, guys, because a square can't be negative. Okay, so this equation has no solution, so this is never true. Since it's never true, the domain of your function here is R, the set of all real numbers. So since it's R, there is no point where the function is not defined, and there is no point where you may have vertical asymptotes. So we can conclude here that there is no vertical asymptotes. Okay? For horizontal asymptotes, we're going to compute the limit as x approaches. I will put plus or negative infinity since I will find the same thing. Since here you can see that the leading terms are x squared and x squared here, so it will give a constant on both plus and negative infinity. So the limit of x squared minus 1 over x squared plus 2. So this limit is equal to the limit of x squared over x squared as x approaches plus or negative infinity, and this is equal to 1. So here you have a common asymptote again. Y equals 1 is a horizontal asymptote as x approaches plus or negative infinity. So we are done. Thank you for your attention and see you in the next videos.